You guys actually want to see cool things. I can go back into this a year show. Touch. Hello, everybody. Once again, my apologies. Here we are. We're going to discuss a little bit about running jobs on a resource. So we're going to discuss some basic concepts of running jobs on a resource, such as batch mode versus interactive mode, key scripting, a little job management and submission, and then we're going to go over a little bit about uniform. And that topic will be All right, so that being said, let's discuss a little bit about batch versus interactive mode. All right, so in interactive mode, you do a Q sub minus I, and then you give it whatever parameters as far as wall time and number of nodes, and so on and so forth. What it does is it takes you from the login node, where you should never be running a job, to an app run or a compute node. At that point, you can either run the job directly, or if you're on a Cray system, when you submit app run blah, 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 it will then farm that out to the appropriate compute node. But again, it's an interactive option, so you're actually there on the app run, on the compute node. That's wonderful for a lot of things, debugging, using a GUI like a debugger or some sort of profiler, some sort of visualization and analysis. It does not ever work so well when you're wanting to run a very long job. For one, if you don't submit through the batch system and your term falls over, lose everything you started, or whatever restart file you had. So another excellent way to run a job, the preferable way, frankly, is the batch mode. And you simply write up the submission script and queue sub that script. And it will then submit that into the batch queue. It will determine the size of your job and the amount of cores, the amount of time you need, which queue to put you in, and then it'll give you priority and submit to the system. Really good because you can do file movement from within that. You can do that actively, but then you have to wait for the program to you type in what you want to be top where, and you actually to do sort of pseudo workflow as far as scripting. CDS. We want to use script to let the scheduler know the resources we need, the settings we want, environment variables, and what is going to be. And you can write this in other different sorts of shells, corn shell, PC shell, what have you. I'll be using bash in these demos. Now, these demos are at a permanent location right here. Okay, Elliot was the professor I had created them for initially. And you find all these either from the training website, or you can go directly on the Kraken or any Nix resource and grab these files. Submission and management. All right, so there's a combination of Torque and MAD. You may have also heard of a program called Slurm or Ceph. These are all the scheduling programs that allow the resource to fill its resources. We'll have to have a weirder way to say it. It allows you to tell what resources you need. So different commands, and I highly suggest going on to this website right here and getting full information as to what sort of modifiers those commands can take, what sort of arguments, so on and so forth. But you'll see the majority ones we're going to mess with are going to be QAlter, QDel, QSub, and QStat. Those are going to be the primary ones that we have to discuss. Before we get to the core, I am going to do some examples. So, first thing I for terminal I have, whether that's Ruby, SQL, PuTTY, what have you. This is a Macintosh. A little larger, so it's easier to see. And I'm going to blow up the font a little bit. Hopefully that's a little easier for you guys to see. All right, SSH to vvitro at say kraken.nix or uk.edu. And I'm going to use my fob here, put in my password. And log in. One thing that's very important to know, you run jobs off of your home directory, NFN directory. Many of you do that, and a few that will, and those that will, would suggest you use a parallel file system. Do can be much more rapid in being able to go out to several OSTs and format each of your files instead of everything going through one controller. So Luster directory. Luster directory, and I am going to excuse me. I need to make a copy of examples over to my Luster directory. Very rare. All right. And let me show this. Okay. So now that I'm in my Luster directory, one of these examples, what you'll see are a number of .sh files. Those are the shell scripts that I'm going to be using to submit batch jobs. And submit a batch job, what it does is it takes that script name and it appends E or O and the number of the job. So you go back then and see the standard error or the standard out as E and O represent, or a given number. Okay. Now, what I want to do is just do a very, very basic, simple MPI script. So I'm going to look at this one, -mpi.sh. So you'll hear, and there are lots and lots of options you can use. You first tell what sort of script it is. It's account, although we have one account, the default account will be used. All right. Now, Kraken, it's important to note that size always must be a multiple of 12. Okay. And wall time. All right. Time is hours, minutes, seconds. So 5-minute wall time. And then I CD to the PDSO working directory. Now, where I am currently submitting this job from, it's going to CD to that directory. And then to do an app run, right, and that's spelled a Cray machine. This is what MPI runs. Give it a number of processors and a couple of programs. And I call it time. Okay? So just take a look at what that would look like as a job. So I would say qsub mpi.sh. It then gives me the job number. Now, was one of the commands, that's the submission command. One of the commands is keep stat. So if we do stat, this huge, completely intractable list. That is everybody that's running on Kraken. It's a lot of folks, right? The thing for you to do is do a qstat minus u. That and your username. Just tell me what it says you can. I have your job number, name, it's a small q because it only asks for a little bit of wall time and key processors. Here's the name of the job, right? It's an ID, number of nodes, number of tasks, and then, or excuse me, that's not number of nodes, that's number of tasks, number of nodes. And the time and the status, this is either Q for NQ, R or C for complete. Right? In this case, it's complete. Select bash mpi.sh .039. Right here, this is simply the output from the just had 204 ranks and a hello world, or 200 ranks. I had to give it 204. No, or 204 cores because that would be multiple 12. I only use 200 of them. And as it gives the hello world information, and then it gives the answer, and this is time. So that's where our output file is. And then we can also look and see if there was anything that printed to standard error. As you can see, in the prints to standard error, the actual timing, because that's what they're routing to standard error. Okay? One excellent situation. Now, one of the other things you can do that's really, you can do this interactively, but I'm going to do it in that form, is I do the sort of script, okay? Except here, I'm giving it some extra information. Now, if I haven't changed anything about the script other than I'm only using 64 MPI ranks instead of 200. Yeah, I need 64 MPI ranks. But then I N4, what does that mean? Well, that means that I want you to put 4 of those on each node. Okay? Now, if I have 64 PI ranks, 4 on each node, and I do a simple division, I get 16. Okay? Number of nodes that I need. It has 12 MPI ranks. So 16 times 12, and I get 92. That is the size of my job. That is the number of cores that Kraken needs to set aside for me. However, I'm using 4 on each node. So this will kick up your SU count. If you're in a situation where you have a very highly memory bandwidth dependent problem, it doesn't matter, because you need to give each of those MPI ranks as much access to memory as possible. Take that layer one step further, right, and use minus capital S. What does minus capital S do? Minus capital S says this is how many I want you to put on each socket, right? So we're at this first, I said 4 on a node. Just so you know, crack node has 2 6-core sockets. So it's going to those sockets and use 4 cores on it and leave their socket completely blank. Because then you still have 4 of 6 processor ranks competing memory bandwidth from one socket. If you want to, you have 2 ranks, which is the normal full complement on a socket gathering information, then you use minus S2, and that's sure everything gets out evenly over the socket. Okay, and again, just Q sub that. And we'll go to that in just a minute. The other significant bit of information, that one more flag you can give after apple. That's the number of threads. Okay? I have not, where is it? Trying to find, there it is. It's like I know. All right. MPI, bash, MPI, socket, thread. You'll know here, what I have done is the exact same thing, exact same code. Okay. I need 16 nodes so that I can have 60 MPI ranks, 4 per node. But then I would like to, the minus D says this is how many of those cores I would like you to make into threads. Here is I have, on a given node, I want 4 ranks, 2 threads. So that's in 4 MPI ranks, or 12 cores. So I will actually be using 12 cores on these threads, or these nodes. Okay? I'll be using all 12 cores on these nodes, except here I'll have 2 MPI ranks and 4 threads on one socket, 2 MPI ranks and 4 threads on the other socket. The previous had given me all 4 MPI ranks on a socket and the threads across the other socket. So those flags did a job using a script. All right, tell it the size of the wall time. You tell it to go to a PBS working directory, and in this case, obviously, you do need to set the open the environment variable, which you do the same way we would do it on a command line. Submit the 2 app records. If I'm on crack, let's say I'm on some other resource that was cray. This is still a cray. All right, so if on a resource that wasn't a cray, a killer situation, then what I mean, let me just look at this batch. This is for cray. Let's say I was on Beacon. Right? Beacon has 16 cores per node. All right, so that's 16. Why? Because that means that I get one node. All right, and then what I tell it to do is, let's say, export 10 thread, and instead of an app run, I run back my N1. What I say is I want you to have one MPI task with 10 threads. That's in the 11 cores used on it. Right. That's only if you're on a machine that's not a crane. Use MPI with app run and some of the nifty little wrappers, thread, the D's, and the F's are not there for you. The very basic how to look at your output from a job. I also want to show you, well, let's look at the output from this other job here too. Let's VI dash MPI socket .sh .o 9. Right? And so you'll know it's a Hello World program. Okay? And interestingly enough, what you'll see here is you'll see on this one and the other one, see this one just give them, number of them per node. And this one spreads them out differently. This is where we use the socketed solution instead of the node solution. Last but not least, let's take a quick look at the interaction. So here I do q to minus 5. It tells me what's being used. I could just add minus a, support, or minus a, whatever I wanted to, and it's going to give me an interactive job. It's a job. The interest of Kraken is you don't notice that you're on a compute node. It's still going to say Kraken TF4 when it comes up. It's now ready. Kraken TF4. But where you are now, if you're not on a login node, you're on an app run node. An app run node can then farm the job out for you. Last one I talk about before I get to Unicore is part right here. We don't use QStat and QSub. I'll show you what QDel and QAlter do. Very brief. All right. So let me just go to, and I'm going to change wall time to something ludicrous, more than I need. 20 hours, right? I mean, this didn't even take 5 minutes. It's more or less 24 hours. So 4 hours and QSub it. I do that, and I'm like, cool. And I do a QStat minus U v vitro, and I go, ooh, wait, I just asked for this really small job to have 20 hours, and so now it's fucking fuel. Crap. What else? A couple options. One is QAlter. All right, if I heard, one of the things to realize is when you give it this command minus L wall time, like you would with sub, all right, when you're not giving it an additional wall time, you're getting the new wall time. So if it's 4 hours and you gave it a new wall time of 2 hours and it's been running for 3, it'll just stop, right? It'll be, oh, you've exceeded the wall time. So be careful about this. You can very easily kill a job. So now change the wall time. Line out which job, right? 332399. Ooh, thank you very, very much. All right, now if we do a QStat minus vitro, you'll see now that it knocked the wall time down to 5 minutes, pop it up in the queue when it ran the job. Okay? Now, this one here, let's see, let me go and I'm going to do one more interactive job to do QDel. I'm going to do Q minus no, actually I have a better idea. I'm going to cut that same one over again for 24 hours. And instead of trying to alter it, I delete it. I'm going to say QDel. All right, QStat minus U v vitro. What I should see is this job that's completed, the standard in job, just trying to reset node. I have the just ran and completed, and then here you see how it was required time 24 hours, but elapsed time 0, and it's completed. That's why I deleted it. I said, oh, I need 24 hours, but actually I don't. I don't even want this job at all, so just go ahead. Okay, the primary predominant nature of how to deal with job submission, job management on seed resource. Now, we stand as the spot. Keep on going. So I'm going to go ahead and discuss core with you guys in the hopes that at some point our runner shows up, and if not, we'll just get a little more uniform. Let's continue. Oh, I thank Tabitha Sam for her help in this presentation. She's one of our experts. All right, so what Unicore is another option other than using the port and web and PBS. So it's what you have is a client that's on your local machine that you download. You get a proxy certificate, allows you access to the machine, and pick a machine and you simply run a job. All right, so some of the components, all right, so you have a registry, which is going to let Unicore know that you have speed and backlight and Kraken and Keeneland, et cetera, and so on, resources that you are available to compute on. All right, you have a GUI, that's client, right, whether that's command or GUI, and authenticates messages and makes sure that it does the most efficient exporting possible. Unicore X acts the job submission, job management, storage access, all that business. And locally, it doesn't run on your client, it runs with the local service provider that the client communicates with. TSI, all right, provides remote interface to the operating system. It lets you know what files you have on the target resource. All right, excellent. Scott is here. So let me briefly do this, and then we'll get him started. So again, here are some of the current resources that exist on Unicore. To grab a My Proxy certificate, one of these .pts12 files, and that is what allows you to authenticate it yourself and get you set to run on all the resources. This is the client, or the GUI client. Okay, you have access to your storage and to all the systems. Again, in this presentation, you'll see these little videos you can actually look at later, but now we're just going over it briefly so you know it exists. Discuss it further depth later. You can even stage stuff through Grid FTP using Unicore. Now, a command line client, all right? The command client takes JavaScript or mission description language, all right? You actually submit a job through the command line instead of using the GUI if that works out better for you, and you prefer that to using a simple QSub and QStat. So information is available by Unicore site, and as well as on the next page. You can email us if you have any questions. And with that, we'll say I will say thank you, and let me take some questions. Anybody have questions for me? Let me turn up my volume. I'll make sure anybody to speak directly. All right, so hopefully that helps you guys get started with the idea of why you have to submit a job. You're not just hopping onto a computer, you're onto a login node that you're sharing with people, and then requesting a reason that you alone will have access. That's what the point of dot submission is. Of course, you can do this, you can do dependency chains from within these bat files. You can do them from within Unicorn. And really here, Summerman also from next is going to show us how to use Eden to do this sort of work for us. An example of a workflow might be I run a code on Kraken and then to post-process on Log. Maybe you guys are getting everybody set up. I'm about to not be the presenter anymore, so thank you very much. And hope you guys have a wonderful rest of your week. Hello, my name is Scott Zimmerman. About kind of doing script level processing, what do you want to call it? So here on the screen is kind of a typical thing that you want to do. To serial, usually serial code or serial scripts, maybe with input parameters or different input files, what have you. So there's lots of names for this kind of programming. Some people call it invariantly parallel. Basically, you have these. Each is just enclosed by itself. There's no synchronization, no communication. So it's called inversely parallel or simply parallel for that reason. It's not complicated. You're just throwing more compute cores at the problem with no organization. Some other people call it you can call coarse-grained parallelism in learn that's thrown out there, or mini-task computing. And this is not your HPC kind of job. But like at Next, we have the resource policy, which is unique in the world, and that operates as a single operating system. So you think of it as just on your laptop, except your laptop would have 1,024 cores and 4 bytes of RAM. Kind of compared. So with Nautilus, you can do a lot of different things you can't do on more typical resource like Kraken, where you do nodes in the cluster.
So a non-app, you can run Math, Python, language C a lot in HPC. You can run the whole machine, and each compute core can access the shared memory. We saw users wanting to do this kind of programming where they had lots of real programs that they wanted to run a lot. Some existing solutions, and there are several for doing this kind of programming. I'll just mention a few here. There's GNU Parallel, which is a widely used utility. You can use it, it gets into the mixed mindset of, you can fill your pipeline of whatever you're doing on the command line very easily, and it allows you to kind of launch your commands to various processors. It uses SSH to do that, so you can do it in your plus setting. The parallel command processor. One of our colleagues, Nick, does the same sort of thing, but this time it actually uses API. So it kind of takes this paradigm that I'm talking about, but kind of is an API kind of thing. So it's more HPC. And of course, there's Hadoop, which you've probably heard of, and this involves a lot more overhead of you have to make your problem fit into this map and Java, and there's a lot of setup and configuration. But again, if you have massively units currently with no communication, and kind of more large scale frameworks like Swift, NIM, another one, and Condor. And these ones to do the kind of computing on disparate systems, where you might, computers located around the campus that are hooked to this network, and these kind of frameworks can allow you to run one job over various computing resources on one network. And it's kind of a bigger thing than we were looking for. We were looking for something simple, mainly very simple for the user to get up and running and run these kind of jobs. So we came up with our own very simple framework, and this is probably most like GNU Parallel, except it does use SSH. Now I'll explain how it works a bit. So back to this, in this case I'm showing a Python script, so we're going to run it 1,000 times, maybe with some different parameters. How are we going to do this? So a lot of users use some different approaches. Want to, of course, write a batch for each individual job, which, as you can probably see, is not preferable. You set this up to generate all these scripts, plus you have to deal, keeping track of all the output as well. And the major drawback to this, of course, is that it does what stuffing the queue. So it kind of hurts people from using the resource. You have jobs waiting in the queue to run. And of course, we do put limits on how many jobs you can run at one time. So you're not getting very good to this. You may run 5 of these at a time when we do the scheduler. But see that sometimes when people try this. Other thing to do is try to wrap everything within one script. So here's a typical PBS. And we run the Python script, say here times, one running in the background. The wait command is again. So essentially giving the ability to place these jobs however it wants to in the background. And so you really guarantee placement here. You're relying on the operating system to do that for you. And of course limited to how many you can put in one script like this. Say you had 1,000 commands you want to run, but there was only 100 available. So these are optimal. So we came up with Eden, which is very simple. This slide kind of explains everything to know to run Eden. So basically, on the left, this demonstrates the run directory that you would set up for your particular run. Say, again, we want to run this Python script. Maybe have 1,000 of these that we want to run. So you simply have a file that lists those commands. MyPy, and some flag. That might be. So you just use commands in a file. And then the next file is your PBS header file, which basically tells the resource how many nodes or how many CPUs you want to use for this job. Examples I'm using plus as an example, so you'll see that PBS is using n CPUs equals 4. On Kraken, it would be size equals some multiple of 12. So that's all you need. There's 2 files in one directory, and then simply run the Eden command and giving it the name of that directory. So this is a simple, very adaptable way to, especially running on HPC if you don't have any experience OpenMP or these things. They simply have, they wheel up their process of running. They already have, which are most likely. So the way Eden works is a master worker framework, which has been a long time. This is not new. But you have a master node, and this would be operating on the login where you submit the job. Communicates with various worker processes, which would be running the compute nodes. So we have 5 workers on the compute nodes, and take turns grab commands from the master and pick them on the compute nodes together until your list of commands is resolved. So the action that goes on here is through sockets. The master process takes care of actually submitting a job to the scheduler, and all that is start these processes, and then over the work communicating through sockets. And here's an idea of what the script would look like to pass it on. You'll see it looks similar to the one I showed earlier. The only difference is commands were running work, and then they are one after another. So like in this, we could have 128 CPUs. That doesn't have to be, I just have 5. So let's say 128 of these workers. We could have all 128 working, and you could have bands, and they could go through with those limited resources. So a brief demo. It's a brief demo of Eden Engine. So instead of actually on a resource, what I've already you could just so the real script, I'm calling it black box because a lot of times we have kind of running this code that's really like a black box to them. They can't get to us. We're just running this instance that does a particular thing. And it's all the black box code does is just spit out copy so it's not compiled. Hopefully this. See that it just fits together. Just kind of a dummy program to show the how heating works. I run this program 24 times. So here's my commands list. Simply the 4 commands that I want to run. Here I'm kind of simulating that there'll be a different file for each one, and you can see how the image numbers increase, and giving it some kind of maybe a threshold flag. So generally users will already have in place a script that will generate list. The question is, how do I run this efficiently? So we make that easy. So there's the list. The only other header for PBS. Here's a very simple one. All of the number of CPUs again using what plus. So I'm 8 CPUs and give it the account number. So place that at the top of our Eden script. And then to run it, you just run the Eden command with the name of that directory. I won't actually that now because I'm not on the machine. Show you what it produces. Behind the scenes, while it's running, we'll see this command underscore done. Complete commands that will write. So if you have a very long run, honest in this way, by checking what's in this done. And here it's the honest 24 commands. Their order that they were, files, order they complete on the data. So if it's done, you will have a file that automatically gives you. So basically, command run, it will be the timings, real-time system time. It will give you anything that went on standard out, anything that went on standard error. This file also gives you the actual command line that it got used. So this is just a quick and easy way to look for any red flags that you need to look for. Any jobs took a lot longer than you thought, or had any errors to look at. This synopsis file of all that, you actually get output to. And let's look at this is kind of what we covered, so it makes this PBS file edits and then to the schedule. You can see the first 2 lines are simply that header that we gave it at the beginning. We just append that to this file. And then this one is specific to Nautilus. It uses this command called dplace. It is specific to the SGI environment on Nautilus. And what it allows you to do is append processes to a particular CPU. So each advantage of that on Nautilus, so in this case we have 8 workers, placing them exactly on CPU 0 through 7. So you need to have a CPU dedicated to each command that you run. And so just run those in the background. This looks just like the scripts I showed earlier. Wait command at the end, and then clean up at the end where there's all the joint statements. So also had some other features to make it easier to go along what we call command. The idea I've already showed in these demos where you have one script, you need a bunch of times with different input parameters. Sweep through a separated. So Eden has this parameter capability where it automatically generates commands for you. Here's just that. This is called a params file. So next we kind of put the template of our command here on the first line, again with black box. We're going to get it. And you can use here dollar sign and a variable will substitute you get into that template. So we want to run through thresholds. Mark I is built-in index command. This is a little bit of different index. And then throwing these other examples of the data. And then we'll simply list all the values that we could have as variables. There are 8 different values for the threshold. You can be either not there, which means null, or you could have a hash array. Same with beta, you could have it either not there, or you can use the flag, and then a couple extra flags. Essentially what this does is you need every possible combination of these parameters. So 8 times 2 times 2 times another 3. So again, I'll just run the individual script that makes it happen within Eden. We'll feed in our params file. It spits out all the possible combinations of those params. So to kind of automate, you can write the command list, and you can run it, all the output for all the various. That is for Eden. Slide just to give you coverage. Eden is entirely in shell scripts. So again, the thing that we wanted is very easy to use. They don't have to do anything. They don't have to compile anything. They can cluster, or they can use it on an existing Nix resource on Kraken or Nautilus. All they have to do is load the module, and it's there to go. Also with shell scripts, that makes it very easy to change around yourself for your particular need, which some users have done, gone in and tweaked some things to make it work for their particular situation. So this just shows the flow of through the Eden framework. The Eden.sh script is the starts everything off. The Atom script, which will take the command, or could have been automatically generated to the param file that is code. And we'll take care of actually writing this EBS script, submitting it to the scheduler report through QSub, and then that script on the compute node over here on the right. And then you see you'll have as many able processes, those are the worker nodes, as you report. And then the lines here are the communications. Those nodes back to Atom sockets. Once your jobs are done, the blue line shows the output into this, and then you process it, and then we'll collect all that information by that. So documentation of Eden on our Nix website. So go to nix.tennessee.edu/Eden. There's detailed examples there of how to use it on Nautilus. It's installed on Nautilus and as well as Kraken for your use there. It's also available on SourceForge, the source there, and that version also has an option to run it on a situation where you don't have a job scheduler. So you run it on your laptop if it has multiple cores or clusters. Okay, that's it for Eden.